So having seen logical identities, meaning logical implications and equivalences, subsequently we looked at a logical argument, couple of arguments, and see whether a conclusion given follows from the premise. And in some of the cases it was true, we attempted using well-known identities and equivalences, and wherever it was false, we attempted a Venn diagram to show or to establish a counterexample. We will see more on that. There is something called scope. For example, when you have there exists x p of x, when you have there exists x p of x and q of x, something like that, we want to know which part of the predicate or the expression the quantifier there exists x, or for all x, it is active. For example, suppose I say there exists x p of x. It's a straightforward one, and this x is associated with this. It is bound to this predicate. Okay, and so the scope of this is restricted to this part. So scope of x is restricted to p of x. So suppose I say there exists x p of x and say q of x. When I say this one is active only over here. X is bound only to this part, and over here x is free. This x is not having any influence on this. However, when I say there exists x, p of x and q of x, please note there are braces over here, which means this x is having control over both predicate p as well as q. So in this x is bound. So in this x is bound to both p and q. So while writing predicates and quantifiers, one has to be careful to which part of the expression the variable that we have chosen, x or y, is active. We may even come across expressions involving the quantifier and non-quantifier expressions, meaning simple propositions. And so x is bound to this predicate, r is a simple proposition. So when you have something like this, then whether you write this is equivalent to writing there exists x, q of x and r. Anyway, r is not having the variable x, so x is only bound to this, and whether you write this one like this or including r, it is not it will not change the meaning. Okay, so now having given this, we will now see how to prove claims involving predicates p, q and some logical operators, which just like the way we have proved a couple of implications and equivalences in the context of ZOL, which we subsequently used while proving logical arguments, things that we are going to prove can also be used. So for all x, p of x and q of x biconditional for all x p of x and for all x q of x. So here is my claim. So you have a quantifier for all which is for both p and q. We want to know whether this quantifier can be distributed to p and q individually, and we will establish a formal proof to show that this claim is indeed true. It is biconditional. Similarly, given for all p and for all q, we wish to know, can we take this for all out and then combine the predicates p and q. And once we are done with this, we will ask, is a similar claim true if the operator is or, if the operator is implication, if the operator is biconditional, and we will also change for all to there exist, and we will do all sorts of experimentation and see which of the expressions are true and false. And if it is true, we will establish a formal proof, and if it is false, we look for counter example, or through some counter example through Venn diagrams or through set theoretic example. Okay, let's look at this part. So which means so when you are asked to prove p biconditional q, so this proof has got two parts. One is assuming p, which is our premise, prove q. This is called necessary condition. Is q necessary for p? Or this also means only if part, because this is what? P if and only if q. Next, what we do is, assuming q, we will prove p. Correctly, yeah? So, assuming q, we will prove this. Correct? So, this is called sufficiency condition, or the reverse direction is sufficiency condition. Okay? This also called if part. If part, and the other one is only if part. Okay? So now in this you are asking, is q necessary? In this you are asking, is q sufficient? You can also ask other way, is p sufficient? Is p necessary? Okay? And so we have two parts. We have to prove, assuming p, prove q. Assuming q, prove this. So this will, in this proof, p is my premise, q is my conclusion. In this, q is my premise, p is my conclusion. Okay? And we are checking whether q is necessary for p, or this also means p only if q. P only if q is if p then q. And in this we are asking, is q sufficient? Is q sufficient for p? That is equivalent to asking p if q. P if q is q imply p. Correct? So this part is p only if q. This part is p if q. P only if q is p implies q, and p if q is q implies p. Okay? So let's look at the forward direction. P implies q, and what is given to us is for all x, p of x and q of x. Now apply the definition. If you apply the definition, we get meaning instantiate with respect to first item, second item, and so on. So you get first element as this, and p of x1 and q of x1 and p of x2 and q of x2 and so on. Because we know for all x, p of x is, so we know that for all x, p of x is p of x naught and p of x1 and so on. Now in this case my p is precisely this. So instantiate with respect to first element, second element, and so on. Okay. So for simplicity, and take the first two expressions alone. Okay. Take the first two expressions and simplify. So you have p of x naught and q of x naught. It's and everywhere. So p of x1 and q of x1. Rearrange the terms, it's all and, right? Associativity. So p of x naught and p of x1 and q of x naught and q of x1. Okay. Now if you bring other terms, so p of x naught, p of x1, p of x2, like that, this will be there. This will be q of x naught, q of x1 and q of x2 and so on. Okay. And this one is simplicity. Pick the first two terms. Then I am rearranging. This one is due to associativity property. Now generalize this to other terms. Fine. Now apply the definition again. If you apply the definition, what do you get? This one is for all x, p of x, and this one is for all x, q of x. This is by definition. So by definition, this is for all x, p of x. This one is for all x, q of x, which is precisely what we want to show. And to establish this claim, and which is true, what we do is apply the definition, and for all x, p of x, so you get this expression. And for simplicity, let me take the first two expressions, rearrange them due to associativity property, and apply the definition again. You see that the claim is true. Fine. Let us prove the other direction, which is q implies p. So again, by definition, for all x, p of x is p of x naught and p of x1 and p of x2, so on, and by definition you get q of x naught, q of x1 and q of x2 and so on. Then use associativity property, and as we did before, just work with the first two expressions so that you appreciate things. So p of x naught and p of x1 and q of x naught and q of x1. Then bring all x naught terms together and x1 terms together and x2 terms together. Now you generalize this. So if you generalize this, this becomes p of x naught, q of x naught, okay, and p of x1, q of x1, p of x2, and q of x2, and so on. Now again apply the definition. If you apply the definition, what do you get? For all x, p of x and q of x. In some sense, you apply the definition and expand, rearrange the terms using well-known properties like associativity, and apply the definition again to get back the generalized expression. And it turns out that sufficiency is also true, which means this claim is true, and we have shown the forward direction as well as the backward direction. In general, if you are asked to show P by implication Q, it has got two parts, or P if and only if Q, it has got two parts. One is P only if Q and P if Q. So establish the proof of correctness and individually for each of the directions. Okay. Please note this. When you are P biconditional Q, this is equivalent to negation P biconditional negation Q. It is there in the scribe, or you can later verify that if you take this and take the biconditional between these two, what you get is a tautology. Which means this one is equivalent to P biconditional Q. So the entire part is P and this part is Q. This one is equivalent to negation P biconditional negation Q. Okay, so which means negation for all x, P of x and Q of x, biconditional negation for all x, P of x and for all x, Q of x. Now simplify. If you simplify, we know if you bring negation, quantifier flips, this becomes there exist negation P of x and Q of x. Biconditional negation for all x, P of x, this one becomes R, negation for all x, Q of x. Then simplify. So there exists x, negation P of x or negation Q of x. Again quantifier flips, this becomes there exists x, negation P of x or there exists x, negation Q of x. Use some change of variable. Change of variable meaning negation P of x is say S of x and this one is say R of x, some predicate. So which means this is also S of x, this is also R of x. This means there exists x, S of x or R of x if and only if there exists x, S of x or there exists x, R of x. So this shows that, and S and R are some predicate. It could even be P, Q and so on. So this also means there exists x p of x or q of x biconditional. There exists x p of x or there exists x q of x. So what is this telling you? With respect to and, you see that for all kind of distributes, for all goes inside. And with respect to R, there exist. So with respect to R, there exists as distributing. So there exists P of x or Q of x is equivalent to there exists P of x or there exists Q of x. So now we want to know and whether this one, a variant of this, suppose I bring R over here, is this true? And suppose I bring AND over here, is the claim true? Which we shall see now. And what we did over here is, we have proved this and we know that P biconditional Q is equivalent to negation P biconditional negation Q. So what we did, and use that, start simplifying it. So bring negation over here as well as over here, then apply the equivalence that we have established before. Negation for all x px is there exists x negation px, bring, and the quantifier flips as you bring negation inside, then apply De Morgan's law, and this one is a predicate, some predicate s, this one is some predicate r, and which means this is the conclusion or this is the claim follows from this. The closely related other two stuff we shall see now.